So let me continue. So last time I was discussing a simple, I stopped when I was discussing simple stochastic particle lattice model. And so what what I will do today probably is finishing discussing this lattice model, the simple one I discussed, maybe a few of the property, and then discuss a bit the notion of weak noise, stochastic processes with weak noise, on how you relate that to large deviation function, and why it applies to this macroscopic fluctuation theory. So I don't know how far I will get if I want to have time to discuss a bit quantum system later on, so maybe I will shorten this discussion. So there was two cases, which was, so again, what we discuss is in 1D, we have a lattice where there is particles, n, so site I, number of particles is ni of t. So the system is of size L, say. So I equal to 0 to L. If there is n sites, L is A, n, with A the mesh of the lattice. And these models are defined by giving some rule for evolution of the density of the number of particles per site. And these rules are probabilistic, so there is some probability that something happens. And from that, you deduce evolution of the probability, and these processes are Markovian because this evolution depends only what happened at time later than t, depends only of what was the configuration at time t, not before. So there was two models, one which was independent random walker. So as it was said, is more or less bosons, and then there is move on each edge of the lattice, independent of each particle can move independently of the other one. And then there was the SEP, where there can be at most one particle per site. So there is some kind of exclusion principle. Classically, this is due to hardcore. Quantum mechanically, it's just Pauli principle, if you think about fermions. And what I didn't say is that this one, actually, just by looking at the evolution, for example, at the mean density in time, you can see that it satisfies, for example, diffusion equation on the lattice with the diffusion constant, which is 1. So they are diffusive, this system. I will not do the computation. This one also is, is diffusive, so it's d equal 1 in some normalization. Actually, it's a constant independent of the density. And then, just for, if you look at the literature, so the parameter sigma, which is here, takes different value in the two models. So sigma depends on the density. Here it's 2n. And sigma here is n1 minus n. Actually, there is a relation between d and sigma. So there is a general relation, which is followed from fluctuation dissipation relation between n, sigma of n, and the free energy. So if you know the free energy and diffusion constant, then you know sigma. So I will not compute them here. I will just give you the definition, and then we will go on. So how you define them? So we are looking at diffusive systems. So, for example, we try to impose a density here, Na. So there is a system here. We impose a density Nb. So it means that if Na is different from Nb, there will be a flux. So there is a non-trivial current. So this means that per unit of time, there is some number of particles which have goes through the system. So if I call Q of T number of particles which have gone through the system, maybe I will. So there is a so this number of particles can be if it's during time t, during time interval t. The number of particles is linked to the flux, to the current. So that will be if we look at if we look at the edge here at point x. We take a x0, and we look at the particles which have gone through this edge at point x0. That will be time integral over time t of the current at x naught of s. And in mean, if it's homogeneous, the current will be independent of x0. So that will be independent of x0, in mean at least. If it's not, then you do average over the system. So that you expect that this will be proportional to t, naively, because there is a flux. So if the system is diffusive, the mean of Q of t over t, let's say, that will be equal to the diffusion constant times minus gradient. So and A minus NB over L. So that's the scaling what you expect. So it's just a Fourier law. The current is proportional to the gradient of the at least I will take NB minus N small. So small compared to the mean compared to NB plus NA over 2, which is what we call N bar. Okay. So just you say that the current is proportional to the gradient with a proportionality coefficient, which is a density. So that's how you will compute to the diffusion constant. That's how you compute the diffusion constant. You put the system slightly away from equilibrium. So last time there was a question about anomalous diffusion. If you have anomalous diffusion, there will be a different coefficient here. And if the system was ballistic, this charge will be just independent of L, the number of charge. So the fact that it's scaled like 1 over L is due to a diffusive system. So that's the definition of the diffusion constant. And the definition of the sigma is related to the fluctuation of this charge at equilibrium. So if you look at qt square, let's say connected if you are close to, but over t, it will scale like t. That will be, for example, for NB equal NA. This will scale also like 1 over L, with a coefficient which will be then the mean density. That's the definition. It's how you compute. And then you compute it. There is fluctuation relation, and you get sigma from that, or you compute it directly.
Yesterday you introduced that independent one of those was scaling with the factor lambda.
I put.
Are sigma related in any way to this?
Yeah, there is a lambda somewhere, so actually you have to be careful, so you put lambda of. Something like that. A square. And then you take the limit. So it's in the continuum limit. Well, just to be the good limit. Okay, so so with tiny exercise, but I think I will not have time. We will be able to derive this quantity from the MFT, but I will not do it. So what you want to know about this system is fluctuation of. So the question we want to know. We'd like to know. Statistical properties of the densities. It means we want to know, so the density are Ni, the density Ni for I equal 1 to N, and we would like to know the statistical properties. So for instance, we would like to know the mean of Ni. So that's what we ask. What is the correlate, the variance of that, etc. N1 and K. Then we can ask more complicated questions, but that's what we would like to know at least. And then, so usually when you have a bunch of random variables, you can introduce the generating function of this cumulant, as we did last time. So all these functions will be so that's a generating function. Of the moments. If you take the log of the cumulants, exactly the way I did it yesterday with the variable, I call it x, I think. So by taking derivative with respect to h, you will have access to all these cumulants, okay? And then, this quantity, instead of, if you do, if you take a continuum limit, let's say a goes to, so in a continuum limit, I will describe it more precisely how is the continuum limit defined. Continuous limit. You can view that as a discretization, as a Riemann sum corresponding to, if the mesh of the lattice is small, as a Riemann approximation of an integral. Okay? So that will be close to integral over dx h of x and x. Well, now h, for example, I am thinking as hi here is h of the value a g over n, where h is a cutoff, and then you have you should have a factor 1 over A here, which is n. Okay? Or if you want to say the integral of dx is A times that. And A, which is the mass of the lattice, 1 over A is n over L. N, and here I divide by. Okay? So what we compute, something which is E and what you will find is that this, what will be fine is that this function actually when n goes to infinity, up, so there is many sides, L fixed, which means that an is fixed. So you take the continuum limit, the mesh goes to 0, the size of the system is fixed. This will scale like n times some function of h of x. So what does it mean? It's exactly the same thing as what I did before. So I had a variable, yesterday, if you remember, I have a variable x, and I was computing the generating function of x with the parameter n, and then 1 over epsilon, and then I was taking epsilon goes to 0. So here, the parameter epsilon, again, is played by 1 over n. So that's analogous to large deviation function with epsilon equal 1 over n. So this means that so this function is a generating function of this correlation. If I have such a formula, so it's not given, it's just because the measures that you compute from these processes. So we look at, for example, I didn't say it, but you should choose the stationary measure. So the measure of the corresponding lattice model. So the stationary measure is the one which is obtained by taking the large time limit, obtained at large time. Which means that if you start with any configuration of density or particles, and you let the system evolve randomly according to the rule you have, it will converge to some distribution of particles. So this distribution, because you have run it during large amount of time, will be stationary, because if infinity plus epsilon plus delta t is still infinity. Okay. So in that system, you have a large deviation function. It's not, so you have to prove such a statement. So it's not given a priori because you define the model and there is no guarantee that you will have a large deviation function. But you have here in that case. And this implies, this is equivalent, as we said yesterday, that the probability to have a given profile, n of x, is of the form exponential n sum. So that's what I call f, some f of n of x. Okay? That's what I was calling I yesterday. And the two are related by Legendre transform. So I am here not proving anything. I just tell you that if you analyze such a system, then you will prove such a statement. I didn't prove it.
What is H?
Huh? What is H? It's a dummy variable. It just, when you have generating function, you introduce variable, such that, well, one purpose of it is that when you take derivative, you will generate. the moment. For example, that's what I was doing when I was computing E of Zx. You take derivative with respect to Z. What you do if you are used to field theory, you introduce a current, okay, G of X, because when you take derivative, you have the correction function of the field. Okay?
Second question.
Yeah.
Above, you wrote this for diffusive systems, and then you wrote this equation like E of Q over T.
Yeah.
So can you explain this equation?
Which one? This one?
Yeah, for diffusive system. So why is this equation?
But, okay, I will try. So I say that Q of T okay. No, let's say. So if I am in a, so I have a flux. So I have a current. No. And if I wait long enough, the current will be independent of time. I have a steady regime. Okay. So on the current J, we know if it's diffusive, this is the density times the minus the gradient of the density. Okay? now what if delta n is small, this one is equal to minus the density. The gradient is what? Is the value of n more than nb over L. No? So that's just what I have written here.
So the right-hand side I understood actually, is the left-hand side I don't understand.
Ah! So we define Qt is integral Ts. Then I go. With respect to some measure, I will tell you later what is the measure. Okay? So this measure, I will use the measure that you get when you let the system run during a long period of time. So it's a steady measure for the process. Okay? So this means this is a steady current. And, okay, so that's the definition of that. It's just the expectation value of the integral of the current. So that will be, because it's steady, this one is steady. Steady. This becomes T times E of G. Then you have to compute G according to the rule that you have defined for your model. It turns out that all the models I have described are such that this G is diffusive. I just claim that this is the output. Yeah.
Here you are computing a steady state current. How would they able to do the same kind of process when we quench a system from an initial rest state to an out of equilibrium state with NA and NB with such a large negation strategy?
I think I didn't get the question.
Well, I mean, here you have NA is equal to 20 in time, and we set ourselves in an infinite time limit in which we will have some steady state parameters. What I'm wondering is if NA depend on T, can we do the same kind of study?
This is not, yeah. What I had in mind here is that NA and NB are fixed parameters, okay? It depends how you inject particles. So they are external parameter fixed. So if they depend in time, there is no guarantee that you will reach a steady state because it depends how they depend on time. So if you are telling me that as they take some value, because you said you quench the system, if you take some initial value for NA and NB, and then at some time T0, you change the value, but they remain constant after that time. If I wait long enough, again, infinity starting from T0 is still infinity. So it will reach a steady state corresponding to the value after the quench.
You cannot do
but if NA varies in time with some frequency, but you will never reach a steady state.
You can't do any large deviation processes in some sense of field theory kind of spirit, where the density of default is n will depend on x and t.
Well, yeah, you probably can look at of time dependent. I believe you can. So I have because of the weak noise. So concretely, I will have to think about how to implement it, but I think you can. Because of the way it is defined from a weak noise stochastic process. So, so in all these models, so what you will know, so if you compute this correlation function, the generating function satisfies a large deviation function, and I think there is two comments which can be made. Is I told you for one variable that if you have a large deviation principle, this implies if there is some analytic property for this generating function, some scaling for the cumulants. And I was telling you that there was this parameter epsilon. Then yesterday I told you if you have x, a random variable x satisfies a large deviation principle, then its n's cumulant scale like epsilon to the n minus 1. So this means that here, if I look at the correlation function, the mean n of x is independent of n. So it's O of 1 with respect to n. And actually, you can guess what it is because you impose a density Na at x equal to 0. You impose a density Nb at x equal to L. And you impose that in the long time there is a steady current. So it means that the current is proportional here, d equal 1. So at least for SEP. So what I'm going to describe is SEP. D equal 1. So the gradient of the density should be constant. So it's a linear approximation between the two. Na times x, then Nb minus Na. X over L. And then, if you look at the two-point correlation function, we know that it's of order n. So it's something, it's O of n, n minus 1. And for SEP, with d equal 1, sigma equal n1 minus n, we know the answer exactly. So it's Nb minus Na square. Then I will take L equal 1 because I don't know it. A mistake. For x less than y. So divide by L properly. Oops, divided by n. So what does it mean again is that the fluctuations are vanishingly, if you look at the variance, all the correlation function will vanish when n goes to infinity. There is some scaling as a function of L. But if you extract this scaling property in L, the correlations are long range. So in field theory at equilibrium, as we discussed last time with Andrea, correlation function decay either exponentially or if it's a massive theory or with a power law. If it's a conformal field theory, it decay. Here the correlation function do not decay with distances. So there is long range correlation function. And that's due to the fact that it's out of equilibrium. And then if you look at all the cumulants, n of x1, n of x to the k, that will be 1 over n to the k minus 1 times some function which is complicated. So the higher order correlation function are smaller and smaller. And actually, usually when you work, you do the opposite. You start with trying to compute these things. If you don't know nothing about the model, that's simpler. And you really realize that there's some scaling in terms of your large parameters or your small 1 over n. And the scaling is not arbitrary. As a function of k, there is a peculiar scaling. And this tell you that there will be a large deviation principle. And then, so as a consequence of this long-range correlation function, this means that this function here, because they are related by derivative, all these functions, W, so F and W, so F and W, are non-local. Whereas at equilibrium, I showed yesterday that this function F was just given by the integral of the local free energy. It was a local function of the density. Now they are non-local. And that's a consequence of this implied by the fact that you are out of equilibrium. Okay, so compared to yesterday, I didn't prove anything, so I just tell you facts. So if you want to prove these things, you have to study either the macroscopic model or you directly start with the macroscopic. In French, it's difficult, microscopic and macroscopic. It's very... So you start from the lattice model, and then you try to compute. That's a bit difficult. You cannot always do it. It happens that some of these lattice models are integrable, so you can solve them exactly. So you compute these things. Or you start directly with a macroscopic theory, which is a MFT. And then using tools from stochastic calculus, you can derive equations for this function. So since this is I call it a ballade, I will use the excuse of that we have a weak noise limit, a weak noise stochastic equation to tell you how to deal with what are the tools you can use to study weak noise stochastic equation. I will do it with one variable. It's easy to generalize to a finite number of variables. And then you will have to admit that you can extend to this infinite number of variables because in MFT, you are dealing with a continuous profile. So now I will spend, I don't know, maybe I will not spend any time. We'll stop. After the break, I will spend half an hour dealing with a stochastic equation, weak noise, and how you deal with that. And then we will.
I have a question.
Yeah, every time you have a question, I don't know how to answer it.
Good question. Like this. So this is somehow a simple model for traffic, okay?
Yeah.
And so I'm expecting that if you increase the flux, at a certain point you get stuck, and then you will have some discontinuity in the profile or some strange phenomena of waves. You don't see this, or you will see this.
I think you see them in asymmetric version of it, ASEP. Well, yeah, when the probability to go to the left and to the right are not the same.
But you have a flux, no?
Yeah, but the dynamic is not the same, and the coarse grain dynamic is not the same. For SEP, when it's symmetric, the coarse grain theory is a diffusion equation, okay? Plus noise because you flush. When for ASEP, huh? Just diffusion, yeah.
But with different regime with respect to free field.
Free field, I don't know what you mean by, but.
Yes, okay.
Yeah, so it's again, I told you, so even at the microscopic level, you can always, so you are.
So you agree with me that a free scalar field is like a Gaussian motion, right? And so to obey the diffusion equation.
Which
Relativistic theory is
in relativistic theory? No.
not relativistic theory is a diffusion equation.
But so we don't agree on the what we speak diffusion. So. diffusion, same thing as equation, at it equation. dTn is dx n, which is not what the relativistic free field will satisfy. Yeah, but there is no. Yeah, there is no I, and there is no 2 either here, okay? And if you think about relativistic theory, there is no 2, factor 2. So that's the question. And again, this is. So in all these models, you can prove that you have an analog. For example, if you look at the mean, if I call in order to ni bar, that's the definition of ni bar, you can prove that you have something like that. N bar bar e plus 1 minus 2 ni bar plus ni minus 1 bar. That's true at the microscopic level for this. But then, okay, we had noise, so that's just for the mean. But no, yeah, it's really not a, it's not really a free field. Yeah. What was the question exactly?
So how would you compare, for example, with the passive scalar? This is also
So, the question was about traffic jam and so on. So if you do the asymmetric one, in some, so you have different parameters. Now you have the way you inject particles, which force a flux. You have the another parameter is the asymmetry. So you have a phase diagram. In some part of the phase diagram, which I don't remember, forget, never worked on it. You have this phenomenon of traffic jam, and actually the scaling limit is the Burger's equation. On the Burger's equation, you have shocks, blah, blah, blah. So it's the Burger's equation.
shocks because how many cars arrive from the left?
Yeah.
They leave on the
Yeah.
other side. So it's
There is no shocks.
fluid.
It's,
Circulation and traffic, as we say.
yeah, everything is super smooth.
Okay. Thank you.
And the passive scalar is totally different. Yeah.
Totally different.
Hmm.
I don't agree, but
Passive scalar, it's passive scalar. So what Andrea refers is you take scalar, which is transported by a fluid. So for example, you imagine that you have a fluid and you inject, which moves, a bit turbulent, and you inject a drop of ink in it. Then the ink will be transported, will diffuse, and be transported by the fluid. Okay, so if I call theta the density of the ink, then the equation is of the form d theta plus u gradient theta, or the opposite, minus kappa delta theta is equal to injection. And it's called a passive scalar because theta is a scalar density. It's passive because it doesn't act on the initial fluid, okay? And that's the density of ink, and that's the fluid velocity. Which you imagine is your water in your bath, which is turbulent. But ink, there is no back action of the ink on the fluid. Okay, that's why it's called passive scalar. So it's a model of turbulence. By the way, turbulence is also out of equilibrium, and as you may know or may not know, there is long-range correlation function in turbulence. Correlation function do not decay as in statistical mechanics at equilibrium. So there is nothing to. It's really different. So what is important in passive scalar is the fact that this one is turbulent. So there is. So it induces randomness on that, but not of the same kind of nature. Actually, in turbulence, you are interested in the limit where this is small compared to that. That's really turbulent for the passive scalar. So what is important is the advection, and the advection should be to the diffusion. That's the analog of having a large Reynolds number in turbulence. So that's what it is. So you forget about that in turbulence, and the randomness and the fluctuation of the scalar is induced by the fluctuation in the field. So it's a different phenomenon. Yeah? Yeah, sure. If I-
So here you're dealing with correlated variables.
Yeah. Highly correlated.
In general, those are hard problems. What will allow you to make this computation is the fact that the scaling of the moments and the fact that you will need only the first few moments to compute that expectation value, right?
Not exactly. So the
When you do it for independent variables, you exploit the fact that the probability density factorizes, and then you
no.
n times the same.
Actually, you can solve this model not because you are just interested in the first few cumulants. You are interested in all the cumulants, depending on the quantity you look at. You can solve the model for two reasons, depending from what you start. If you start with the lattice model, you can solve the model because it happens that it's an exactly solvable model. So why it's an exactly solvable model is that all these models are Markov chain, as I told you. So there is a matrix which tells you how the probability evolve. So it's a matrix, a large one. And to solve the model, you have to know something about this matrix. Its eigenvalue, blah, blah, blah. Eigenvectors, for example, the invariant measure, the one which is a steady, will define the steady expectation value, this measure is the eigenvector of the matrix with eigenvalue 0. So you can solve the model when this matrix is in the integrable class. So it's like an Hamiltonian, but it's not exactly it. It's not necessarily Hermitian, it happens that it is, blah, blah, blah. But you can use the technique of integrability to diagonalize this matrix and to know something about the eigenvector. So that's why you can solve the model exactly in that case. Then if you start from the continuous formulation, which you can solve them because you use a weak noise technique I am going to explain. And then I told you that the moments are very small, but because I look at the density. For example, if I look at the random variable, the number of particles in a sub-interval of the system, I will have to solve this sub-interval scale with n. There is, so if I look at number of particles in that interval, okay? So here it's L between point x naught, let's L over 4, L over 8, I don't know, L over something bigger, 4, okay? So when n is large, there will be a large number of sites. So I will have to sum the local number of particles. So this will introduce an extra factor n. And actually, these cumulants will not be small anymore. So at least they will not, so they will be the 1 over L, but they will not decrease 1 over n to the k. So, so you solve the model not because you are just looking at the first few cumulants to know everything. You are demanding a lot. But there is techniques.
Okay, let's do a short break.